This Zoom session is being brought to you by the Fractal Eternity. All right, for today, we finish off chapter 1, which means that chapter 1 is due via the inbox next week, more or less. I do give some slack, but yes, next week. So, given a function, f of x, its inverse, written f to the -1, f inverse of x, undoes what f does. I'm not entirely happy with this notation, by the way, because it makes it look like it's the reciprocal of f. Not really. It is an inverse, so in that sense, a -1, but it is potentially confusing to call it, write it like that. But still, it's the inverse function. The inverse function undoes what a function does. So that, for example, so the f inverse of f of x is x, and f of f inverse of x is x. So wherever x go, we're given f sends it to someplace. Well, f inverse will send it right back. Another way of phrasing that is that y equals f inverse of f if and only if f of y equals x. These are two equivalent ways of saying that. So, for example, if f of x is x plus 7, then its inverse function is x minus 7. The inverse of adding 7 is subtracting 7. If g of x is 2x, then g inverse of x is x over 2. The inverse is doubling is halving. If h of x is x cubed, then h inverse is the cube root of x. The inverse of cubing is a cube root. And vice versa. The inverse of x minus 7 is x plus 7. The inverse of x over 2 equals 2x. The inverse of the cube root of x is x cubed. Now here's a graph of y equals x plus 7. Here's a graph of y equals x minus 7. Note that, and this dotted line is the graph of the line y equals x. Notice that these are symmetrical around it. Here's a graph of y equals 2x. Here's a graph of y equals x over 2. And again, it's symmetrical to the diagonal y equals x. This here, n-shaped graph, is a graph of y equals x cubed. This S-shaped graph here is a graph of y equals cube root of x. And again, you can find each from the other by flipping through the diagonal. That's a general rule, of course. Given a graph of function y equals f of x, then the graph of x equals f of y is the same as the graph of y equals f inverse of x. Now, x equals f of y and y equals f of x are basically the same equation, only x and y are interchanged. And geometrically exchanging the x and the y-axis is the same as flipping through the diagonal. So the graph of the inverse of f is the graph of f flipped through the diagonal. That's a cheap and simple way to find inverse graphs. There is a potential problem to show, and I'll get to that in a few moments. The inverse of f, its formula is found by writing x equals f of y, and then solve for y. So basically, every inverse function is basically the same as one long algebra problem. We sort of transpose f to the other side of the equation, and it becomes f inverse. For example, here f of x equals 1 plus the cube root of 2x. Find the inverse. Well, if y equals f inverse of x, then f of y equals x. So plugging in y into this equation, putting a y wherever the letter x appears, you get 1 plus cube root of 2y equals x. Now the trick is to solve for y. Well, okay, you do algebra. First, there's this plus 1. We subtract 1 from both sides. Get cube root of 2y equals x minus 1. Then here on the left side, the last thing done to y, I mean, we take y, we double it, we take the cube root. The last thing is the cube root. The inverse of that is cubing, so cube both sides. And get on the left 2y, and on the right x minus 1 cubed. And finally here, the inverse of doubling is halving, so we halve both sides. We get y equals x minus 1 all cubed, all divided by 2. And that's the inverse function. F inverse is x minus 1 all cubed, all over q. Now here's a curious fact. Look what happens with the first function, the 1 plus cube root of 2x. It starts with x, then it doubles it to get 2x. Then it takes a cube root to get the cube root of 2x, then adds 1 to get 1 plus the cube root of 2x. That's f of x. Whereas the inverse function, it works in the opposite direction. It starts with x, subtracts 1, x minus 1, takes a third power, that's the cube of x minus 1, then divided by 2, that's half of the cube root, the cube of x minus 1. Notice that these are all three inverse operations, and they're done in reverse order. Times cube root 1 plus minus 1 cubed divided by 2. So inverse functions are opposite operations in the opposite order. When I put on my shoes, and so when I put on my shoes and socks, first I put on my socks, then I put on my shoes. Then in the evening, I take off my shoes, and then I take off my socks. One morning I woke up so early that I put on my shoes and socks in that order. And I looked at my feet groggily and said, no, that's not right. All right. Now here's a problem. When we go back to flipping to the diagonal, there's a problem. Let's take this graph of this function y equals x cubed. When we flip to the diagonal, we get this graph, which is here the upper half is the graph of y equals square root of x. The lower half is a graph of y equals minus the square root of x. This is not a single function. It is two functions, plus or minus root x. So we have a problem in that this function here does not have a single inverse, it has two different inverses. And that's a problem. We're not defining a unique inverse function. The problem with this function here is that it's not what we call one-to-one. Two different inputs will yield the same output. So inverting is a problem. We call a function one-to-one if different inputs give different outputs. So if A is not B, then f of A is not f of B. Now we can define a single inverse for a function if and only if it's one-to-one. And that in turn, if and only if it passes what's called the horizontal line test. The idea of a horizontal line test is that every horizontal line passes through the graph of the function at most once. Here, however, it fails the horizontal line test because here's a line that passes through it twice. And okay, back here, y equals x squared. This too fails the horizontal line test. 2 squared is 4, negative 2 squared is 4. So if you invert, then where should 4 go? Plus 2 or minus 2? That is the problem. So for example, here's a function. It's called an exponential function of the sort we'll be seeing a lot more of later. Is it one-to-one? Yes. Every horizontal line passes through it once, at most once. These lines less than 0 don't pass through it at all. Here's a function. Is it one-to-one? Not at all. This line passes through the graph twice. So does this. So we cannot define a unique single inverse. All right. How does one invert a function? Well, let's start with f of x equals 2x minus 1. How to invert that? Y equals f inverse of x means f of y equals x. So we put a y in here and get 2y minus 1. That equals x. Now starting from here, we solve for y. We add 1 to both sides. 2y equals x plus 1. Divide by 2. Y equals x plus 1, all that over 2. And that's the inverse. Inverse of f inverse of x equals x plus 1 over 2. Now notice that here, this business is about opposite operations in opposite order. Here, f takes x, doubles it, and subtract 1. Here, f inverse adds 1 and then divides by 2. Here, it's a little more complicated. We can't really do opposite operations in opposite order because here f occurs twice in this expression. Inverse f of x equals x plus 4 over x minus 3. So y equals f inverse of x means that f of y equals x. Fine. So plugging in y into here, get y plus 4 over y minus 3 equals x. And now we're to solve for y. Okay, this is a little more complicated than the previous ones. First, there's this division sign. Division's annoying in general. Of all the 4 operations, it's the most troublesome. So let's get rid of it by multiplying both sides by y minus 3. So y plus 4 equals x times y minus 3. Okay, a distribution is called for. Y plus 4 equals x, y minus 3x. And now we have y's on both sides of the equation and terms without y on both sides. We want all the y's on one side and everything else on the other side. So I'll transpose the 4 to the right by subtracting 4 from both sides. We'll transpose xy to the left by subtracting xy from both sides. Then we get y minus xy equals minus 3x minus 4. Okay, these two terms have a y in common. Let's factor it out. Y times 1 minus x, that equals minus 3x minus 4. Now we divide both sides by 1 minus x, and we get y equals negative 3x minus 4 over 1 minus x. And there's your inverse. F inverse of x equals negative 3x minus 4 over 1 minus x. There you go. Here, to invert the fifth root of x minus 7. Okay, f of y equals x, fifth root of y minus 7 equals x. Solve for y. Okay, first thing, look at the outermost layer of the function, it's the fifth root. Its inverse is the fifth power. So we take a fifth power of both sides. Get y minus 7 equals x to the fifth. Now I'll transpose the 7 by adding it to both sides. So y equals x to the fifth plus 7. So that's your inverse. X to the fifth plus 7. And again, opposite operations in opposite order. Here we subtract 7, then take a fifth root. Here we take a fifth root, then add 7. Now here again, we're going to invert this kind of function, which incidentally is called a linear fractional function. It's a ratio of linear functions. All right, so as before, y equals f inverse of x means f of y equals x, and plugging in y into the equation, get y plus 1 over y minus 3, that equals x. And from here, we solve for y. And as before, we transpose y minus 3. Y plus 1 equals x times y minus 3. We do some distribution. Y minus 1 equals x, y minus 3x. Okay, we transpose the xy term to the left by subtracting xy from both sides. We transpose 1 to the right side by subtracting 1 from both sides. And after that, we get y minus xy equals minus 3x minus 1. Here on the left, y occurs in both terms, so we factor it out. Y times 1 minus x equals minus 3x minus 1. Divide by 1 minus x. Y equals minus 3x minus 1 over 1 minus x. That's f inverse. And whoops, have I? Oh, no, it's not quite the same. It was a closed function, but not the same. Here we have the Fahrenheit to Celsius conversion. If it's F degrees Fahrenheit and hot, then the Celsius measure will be 5/9 of F minus 32. Okay, Fahrenheit to Celsius. So, okay, for various values of Fahrenheit 59, which is comfortable. Then what's the Celsius? That is -4, which is below freezing. There's a shudder. What's the Celsius? And find F in terms of C. All right, plugging it in, easy enough. If C of 59, you just plug in 5/9 of 59 minus 32, which is 5/9 of 27, which works out to 15 degrees Celsius. So 15 degrees Celsius is comfortable, but a bit cool, 59 Fahrenheit. C of -4, plugging it in, 5/9 of -36 is -20. -20 Celsius is definitely cold because it's definitely below freezing. 0 Celsius is freezing point. Now here we have to find F in terms of C. We start with this, and we solve for F. This is 5/9, multiply both sides by 9/5. So 9/5 C equals F minus 32. We add 32 to both sides and get 9/5 C plus 32 equals F. That's how you convert from Celsius to Fahrenheit. Okay, here's a function graph. The graph its inverse. Well, we flip it to the diagonal like that. There you go. Okay.